Hello, I'm Richard Young, your host with Facundo Batista and Kalen Overholt for MIT's course on COVID-19, SARS-CoV-2, and the pandemic. The purpose of this course is to learn what we know today about the virus and the pandemic from the world's top scientists. Today, I have the pleasure of introducing you to one of the world's top scientists, a leader who has helped guide the world through multiple pandemics, Dr. Anthony Fauci. Dr. Fauci is director of the National Institute of Allergy and Infectious Diseases at the US National Institutes of Health, where he oversees an extensive research portfolio dedicated to preventing, diagnosing, and treating infectious and immune-mediated diseases. Fauci has been a key advisor to 7 presidents on global HIV/AIDS issues and on initiatives to bolster medical and public health preparedness against emerging infectious disease threats, such as the pandemic influenza and COVID-19. As an HIV/AIDS researcher, Dr. Fauci has been involved in combating AIDS since it was recognized in 1981, conducting pivotal studies that underpin the current understanding of the disease and efforts to develop therapies and tools of prevention. He was one of the principal architects of the President's Emergency Plan for AIDS Relief, which has saved millions of lives throughout the developing world. Dr. Fauci is a member of the US National Academy of Sciences, the US National Academy of Medicine, and many other professional societies. He is the recipient of numerous awards for his scientific and global health accomplishments, including the Presidential Medal of Freedom, the highest honor given to a civilian by the President of the United States, the National Medal of Science, and the Lasker Award for Public Service. Tony, thank you for taking time out of your busy schedule to speak to MIT students and the many others who are participating in our course today.
Thank you very much for that very kind introduction, Professor Young. I'm really very pleased to speak with you today about COVID-19 in 2021 and lessons learned and remaining challenges, as shown here on this first introductory slide. So I'm going to talk about a number of aspects of these lessons and challenges. I've divided it up into 7 quick components, and I will emphasize the salient features of each of these. So let's start right off with the epidemiology. As we all know now, this is a novel coronavirus, which has actually been recognized in the very first weeks of January 2020 from pneumonia cases that likely were occurring a month or so before, predominantly in the Wuhan district in central China. If one looks at the global impact now from those very few cases that were first noticed in December of 2019 spilling over into January of 2020, there are now in the middle of a full-blown pandemic, the scope and impact of which is unprecedented over the last 102 years since the now historic pandemic of influenza in 1918, with 226 million cases and over 4,600,000 deaths globally. We in the United States have been among a handful of the most hard-hit countries in the world, with over 40 million cases, and at the last count, about 660,000 deaths here in the United States, with somewhat of an uneven distribution of cases, as shown by the progressively darker shades of blue on this slide. We've had an interesting pattern of disease that reflects somewhat patterns in other countries. You recall our first experience in the late winter and early spring of 2020, which then came down a bit, but then surged again in the early summer. In the green arrow, came back a bit, and then we had a massive surge in the late fall and early winter of 2021. The cases stayed up for a while at levels of a few 100,000 cases a day, then came back down, but disturbingly never came down to a baseline that we felt was acceptable to have us keep going in the right direction. Things looked good. You remember the 4th of July when we felt that we would be now on a pathway to resuming normal activity. However, the Delta variant had something else in mind for us, and as shown in the circle on the far right of the slide, we began yet again another deep inflection of a curve of a surge, leading to an average on a weekly basis about 160 to 170,000 cases per day. Fortunately, that is beginning to just start to turn around a bit now, but we are still in the middle of a Delta predominance. Let's move on to the virology. As we all know now, this is a beta coronavirus. It's the same subgenus as we see in many bat viruses. It's an RNA virus with a relatively large genome, 4 structural proteins, the most well-known and studied of which is the S or spike protein containing the receptor binding domain, which binds to ACE2 receptors on a number of cell types in the upper and lower airway, the gastrointestinal tract, and on some endothelial tissues. Transmission is now relatively well understood after so many months of experience. And the transmission is predominantly by exposure to respiratory fluids, not only respiratory droplets, which we thought in the beginning, but now clearly inhalation of aerosol particles. These are deposited as droplets and aerosol particles on the mucous membranes of the mouth, the nose, or the eyes. Transmission is much, much less common through contact with contaminated surfaces and fomites. The greatest risk, as we know now, is indoor in enclosed spaces with poor ventilation, and curiously, in certain behaviors, such as exercise, why gyms are such a risk, singing, why choruses and choirs are such a risk, as well as prolonged indoor exposure. There are some unique aspects of this virus, relatively speaking to other viruses. At least 1/3, and likely more, of people never develop symptoms at all, and up to 60% of the transmissions result from a transmission from an asymptomatic person to an uninfected person, either someone who is pre-symptomatic and will soon become symptomatic, or an individual who will never develop symptoms. Diagnostics are now well known and used widely, the most common and sensitive of which is a molecular test looking by PCR at genetic material from a nasal swab. Tests that are being more frequently used now for surveillance are antigen tests, which detect proteins from the virus, and now a more widely used antibody test to determine either prior infection or, as is being used by many now, to determine the level of antibodies following vaccination. Clinical course, in many respects, is protean and complicated. I just told you that a substantial proportion of people get no symptoms at all. But those who do have a clinical presentation rather similar to a flu-like syndrome with signs and symptoms as delineated on this slide. One unique aspect is a curious loss of smell and taste, which precedes the onset of respiratory symptoms and actually may persist following the apparent clearance of infection. For those who do get symptoms, about 80% of them are mild to moderate, whereas 15 to 20% are severe or critical, leading to a wide range of case fatality with the mean of about 2.3%, but as high as 20% for those who ultimately require mechanical ventilatory assistance. The people who are at increased risk for severe COVID-19, it's very clear from the profile of illness in this disease, where older adults, particularly the elderly, 75, 80, 85 and above, have an increased risk for severe illness. And people of any age with certain underlying medical conditions. Of note, obesity ranks very high up there as a high risk, as does underlying respiratory disease, chronic obstructive pulmonary disease, cardiovascular disease, diabetes, neurological diseases, and a variety of other debilitating diseases. Those who do go on to get severe disease, their clinical course is generally dominated by the acute respiratory distress syndrome. However, as experience has accumulated by literally millions of patients over the last 20 months, neurological disorders, cardiac dysfunction, acute kidney injury, and others are also present, as are interesting situations such as a hypercoagulable state, and particularly in late disease, hyperinflammation, which, as I'll get to in a moment, can actually be treated by blocking an aberrant inflammatory response. There's a curious multi-system inflammatory syndrome seen in children, usually a couple of weeks after the acute illness. We now have thousands of cases reported, and this could be a very serious disease in children. In addition, there are post-COVID-19 conditions that you could generally divide into two buckets. There are those who have severe organ system dysfunction, such as lung disease that destroys lung tissue. These people who have residual disease, this can be directly explained by recognizable organ system damage. But there's another syndrome in which the signs and the symptoms are not completely explainable by anything that's a readily apparent pathogenic process. And this is referred to as long COVID. And some of the commonly reported signs and symptoms are an extreme, sometimes debilitating fatigue, unexplained shortness of breath, muscle aches, dysautonomia, characterized by temperature dysregulation and unexplained tachycardia, sleep disturbances, anxiety and depression, as well as a condition referred to by many as brain fog, or a clear inability to focus or concentrate. We are currently now at the NIH instituting a wide series of cohort studies to examine the pathogenesis and hopefully treatment of this disturbing syndrome. Moving on to therapeutics, the general approach is either to target the virus, and by a variety of clinical studies, some like remdesivir, which is an antiviral used in other infectious diseases, has received FDA approval. Among the most promising interventions that have received emergency use authorization are combinations of monoclonal antibodies, as shown on the slide, for example, those from Regeneron, Lilly, GSK and Vir, and others. Less efficacy, although it has received an EUA, from convalescent plasma. In addition, as I mentioned a moment ago, for those individuals who have an aberrant or uncontrolled hyperinflammatory or immunological response, commonly used interventions like dexamethasone have proved to be quite effective in people with advanced disease, including those requiring mechanical ventilation. Other drugs that block various aspects of the inflammatory response, such as tocilizumab and baricitinib, have received emergency use authorization. And then again, adjunctive therapeutics such as anticoagulants. We are now putting a big push on the identification of vulnerable targets in the replication cycle of the virus in order to design drugs to inhibit vulnerable targets. And this is very, very similar to what we did in a highly successful endeavor years ago that continues to the present time, to use an approach that we used with identification of vulnerable targets of the HIV replication cycle, leading to combinations of highly successful antiretroviral drugs that have transformed the lives of HIV-infected individuals, as well as a similar process that was used for the development of novel antiviral therapies for hepatitis C. And so we are hopeful that this approach will, in fact, lead to therapies that can be given early on in a relatively short period of time, measured in days to weeks, to be able to suppress virus from going from the upper airway to involving multiple organ systems, particularly the lung. Now let's spend a little bit of time on a very important component of the response of countermeasures to COVID-19, and that is in the arena of vaccines. There is a very interesting story behind the highly successful vaccine approach, and that really bespeaks the importance of decades of investment in basic and clinical biomedical research. As I wrote in a commentary several months ago last spring in Science, that the speed and efficiency with which these highly efficacious vaccines were developed and their potential for saving millions of lives are due to an extraordinary multidisciplinary effort involving basic preclinical and clinical science that had been going on out of the spotlight, under the radar screen, literally for decades before the unfolding of the COVID-19 pandemic. And so the objection to the vaccines having been done too quickly and perhaps cutting corners just is not true, because the investment in science is the reason why we were able to do it so quickly. So let's take a look at this particular approach, and we can best do it by looking at the vaccine construct, which has two components to it. The vaccine immunogen, a very important scientific story behind that, going back to the structure-based vaccine design that actually really came into its own, even though it's been around for a while. It came into its own in the study of the envelope trimer of HIV in an as yet unsuccessful, but hopefully not for long, unsuccessful attempt to develop vaccines for HIV, starting off with a stabilized prefusion trimer of the envelope to be the primary immunogen to induce broadly neutralizing antibodies. That eloquent technique was actually utilized predominantly by members of the NIAID Vaccine Research Center particularly with Dr. Barney Graham, whose main interest had been respiratory syncytial virus, he partnered with the structural biologists at the Vaccine Research Center and used the approach to find the right way by mutations to stabilize the prefusion F protein of RSV that turns out to be an extraordinarily good immunogen that is now leading the way to the development of an RSV vaccine. When MERS came along, that same approach, particularly with people like Jason McClellan and Barney Graham and others, who then developed by structure-based vaccine design the beginnings of a vaccine for MERS, which is still in the process of being developed. But when SARS came along, the combination of people who were collaborating for years, Graham, Andrew Ward from Scripps, Jason McClellan, Barney Graham, and others, who used the mutations that were used to stabilize the proteins and the spike of MERS quickly, within days, used the sequence that the Chinese published on a public database to develop the right conformation of the prefusion spike protein, which has been used now as the immunogen for virtually all of the successful vaccines that are now currently in trial or already approved. But also, it was the vaccine platform that really was an important contribution to this. And these are some of the vaccine platforms that are being used for this and other vaccines. Genetic ones like DNA, and most recently and successfully mRNA, viral vectors such as adenovirus, recombinant proteins with and without adjuvants, nanoparticles, VLPs, and others. One example is the use of mRNA. There have been a number of extremely important discoveries, one of which was that of Katie Carrico and Drew Weissman, who showed how to modify mRNA without triggering key inflammatory pathways, namely overcoming a key hurdle that paved the way for current vaccines. In addition, Dan Baruch up at Harvard had been working for years with HIV on a human Ad26 vector that has proven to be very important with other vaccines and is now, as you'll see in a moment, been used in a couple of the successful vaccines for SARS-CoV-2. These are the vaccines that are being pursued here in the United States. 3 separate platforms: mRNA, adeno, and recombinant proteins. 6 separate developers. As you can see on the right, the Moderna has received an EUA and likely soon a BLA. The BioNTech Pfizer has already gotten approval with the BLA, and the J&J has an EUA. The others are not too far behind in the process of getting approval. So let's look at these vaccines in 3 separate areas: efficacy in clinical trials. Probably most of you have heard about that both the Pfizer and the Moderna product have a high degree of efficacy in the clinical trial, 94 to 95%. J&J, a little bit less, but nonetheless still a high level of efficacy against clinically recognizable disease, 72% in the United States. When you look at the effectiveness in the real world setting, the data actually are just as good. Here are just some examples of over 23,000 employees at the University of Texas Southwestern showing a remarkably low infection rate of 0.05% among fully vaccinated employees, and the CDC has shown a number of studies in various reviews showing a very, very high effectiveness of the vaccines. Studies from Israel on observational studies using national surveillance data, again, across the board. Here in this study with the beta variant, namely the 117, showing high efficacy from January to April. Now, I put a caveat there because that antedates the Delta variant, which we'll get to in a moment. But as you can see, it protects highly against early disease, symptomatic disease, hospitalization, and death, and it protects against all the different age groups, as shown here on this slide. However, variants had something else in mind, particularly the highly problematic Delta variant, which from the time of early spring to the present totally dominates the isolates throughout the world, particularly in this country, with 99.3% of the variants being Delta. At least 146 countries now have Delta in their country. Why is it important? Its transmissibility is very high, considerably greater than the Alpha variant. The viral loads in people who do get infected are literally up to 1,000 times greater than the Alpha variant. So the Delta variant is highly problematic. And when you look at the effectiveness of 2 doses of the Pfizer against Alpha, which is in blue, and Delta, which is in red, you see the beginning of a diminution of protection in England, Scotland, and Canada, particularly against symptomatic disease. And then in Israel, a dramatic diminution, what looks like it's holding up when you're looking at hospitalizations or death. However, most recent data from Israel, which we are literally examining in real time now, are showing a diminution in protection, not only against infection, but against serious disease. The Delta variant now may actually have an increased risk of more severe disease. We're getting some reports, for example, from these studies, but we want to confirm it before we make a definite conclusion. This is important because this is the beginning now, as you go beyond April into June, July, and August, and you see, even in a fully vaccinated Israeli population with Delta wave, that the number of severe cases are going very high up, as shown by the red curve, indicating that the protection against severe disease by the vaccine is clearly waning as you go further out from the people who were vaccinated early on in the outbreak. In our own studies shown here from the CDC cohorts, again, a diminution over time in effectiveness against infection and the beginning of a suggestion of a diminution against hospitalization. The most recent data, which are just being examined by the FDA, show that, in fact, this is continuing to diminish, which brings up the question of booster shots for SARS-CoV-2 vaccination. The immunological basis supporting mRNA immunization can be divided into 4 separate components. The antibody levels decline against all the variants, as shown on this slide, using a pseudovirus neutralization. When you're looking at correlative immunity, as shown in the dark black line, that at around a neutralization titer of 100, you get a good protection of about 91%. As you go further down, as you can see, a dramatic drop, and it continues to go up. The line is rather flat as you go from left to right, but it goes up anywhere to 96 or more. Clearly, you need a higher titer of antibody when you compare the antibody titer used to neutralize in a pseudovirus assay D614G in the open circles, and in the same person in the pink circles, the Delta variant. That's for Moderna. Pfizer is about the same. Now, importantly, when you boost an individual with a third shot of Moderna and look at the different isolates, look at the D1, which is just before you give the third dose, and D15, which is 15 days after the third dose. Dramatic increase in immunogenicity as measured by neutralization titers. Delta is not shown here, but the data are identical for Delta. If you look at the Pfizer BioNTech, here it shows against Delta. And as you can see, the same thing, post-dose 2 followed post-dose 3, a dramatic increase in the neutralization titer as shown here. So the real question that we're dealing with now is a booster shot a luxury as a boost for a vaccine regimen that's waning, or is the third shot booster actually what should be part of the original vaccine regimen? And the reason we started with 2 doses is that we needed to get the vaccine out there quickly to save millions of lives, which it already has done. But when we ultimately get down to looking at this as the dust settles, it is my opinion, and now many of my colleagues, that the proper complete regimen would be a 3-dose regimen as opposed to a 2-dose regimen. This is not novel. There are a number of examples of vaccines with multi-dose primary series, including hepatitis B and others shown on this slide. Now, when you look at the Israel data, they do have data coming out in real time that after the booster dose, I showed you the antibody titers, but the relative risk of confirmed infection and severe illness is decreased by more than tenfold with the BioNTech third shot boost. And when you look at the possibility of testing positive, 7 to 13 days after the boost, it's as high as a 68% reduction. And 14 to 20 days after the boost, it's as high as 84% reduction. Now, I can't address that subject without pointing out that it is extremely important from an ethical standpoint that if you are going to boost in countries that have the benefit of having vaccines readily available, you've got to simultaneously provide doses to countries like those in Africa, which you could see on this slide, have a relatively small percentage of the population that's received at least 1 vaccine dose compared to countries such as those in Europe, North America, and South America. And for that reason, the United States has already given 130 million doses to 90 countries and will be giving over 500 million doses starting literally now, 200 million of which will go by the end of this year, an additional 300 million in the first half of 2022, in addition to a program that you'll be hearing about soon of dramatically increasing the capacity of countries to donate and give to the developing world literally billions of doses of vaccine. So I'll close with this cartoon of what we really are in, and namely a race between our ability to vaccinate and the ability of a virus, if left to replicate and spread in the community, will continue to challenge us with mutations and perhaps even variants that might ultimately escape the protection of vaccines. And for that reason, it is even more compelling for us in this country to get those 75 million people who are eligible for vaccines and not vaccinated, to get them vaccinated, as well as simultaneously providing vaccine doses for the rest of the world. So I'll stop there and thank you for your attention.
Tony, thank you so much for this valuable lecture. And the students have a variety of questions. If you have time
Sure.
to answer these. First of all, let me remind you that you and I met very early in the AIDS pandemic when David Baltimore, Bruce Walker, and I were a member of one of your vaccine development programs for AIDS. And we failed at our primary mission there to develop a vaccine. I see that we still have not developed a vaccine that's efficacious against AIDS. And I was curious, do you see anything in the ability to develop highly efficacious mRNA vaccines that might be useful for HIV/AIDS?
You know, I really do. As you know, we've had disappointing results in the non-neutralizing antibody approach that emanated out of the RV144 and then went to studies and large trials in sub-Saharan Africa, the most recent of which just literally a few weeks ago showed a 25% efficacy with the confidence interval which went below 0. So that study was in essence not a successful study. I believe the combination of newer platforms, particularly mRNA, may give us, you know, a new lifeline, as it were, on vaccines. And there's a lot of interest in applying some of the important, you know, it's very interesting, Richard, because we used the structural biological approach that was unsuccessful yet, I say yet, to develop the right conformation of the stabilized trimer for neutralizing antibodies for HIV. But that approach was the approach that got us successful vaccines for SARS-CoV-2. Hopefully it'll go back and rebound back to HIV, and the approach that was used in COVID-19 might help us with HIV. So I'm, in my usual manner, and cautiously optimistic about that.
That's great. Cassandra is asking, it makes sense how underlying respiratory conditions would put people at higher risk for COVID-19, but how does obesity increase one's risk?
Great question. Cassandra, what we know of all diseases in which the respiratory system is involved, the mechanical inability to move air in your lungs by the clear obstruction that truly obese people have in moving air up because of the obesity that restricts the movement of air from the diaphragm as well as the respiratory muscles, that makes a huge difference when it comes to whether or not you recover from a respiratory-borne illness, which is the reason why not only with SARS-CoV-2, but with any types of pneumonias, obese people have much more of a problem than people who can freely move air in and out of their airways.
And Henjan's asking, can you compare the benefits of being vaccinated with the 3-dose regimen with the potential adverse effects, the risks associated, for example, with myocarditis or immune thrombic events?
And the answer is yes. They've been looked at quite carefully, and all the data that we have thus far for the 2-dose indicates that the risk benefit ratio weighs heavily in favor of the benefit in the populations. And remember, the populations that are at risk for myocarditis are younger male, dominantly those, and those who have thrombocytopenia are predominantly women who have that. In general, if you look at the early data from the 3-dose regimen from the Israeli study, it looks good, but I can tell you we need more to confirm that third dose, particularly in younger individuals, we're not concerned at all with an mRNA in older individuals or in women. It's the younger men that you're concerned at, men from, 15, 16, 17, up to 30, 35 or more, because that's where the myocarditis really clusters. Thus far, the Israeli data look good, but quantitatively, we need more before we can feel comfortable to answer Han-Jin's question comfortably.
Knowing what we know now, what is it about this virus that explains the high frequency of asymptomatic disease? Is it related to viral load correlating with severity of disease?
That is the question that, as a virology immunologist that I am, that completely stumps me. I have not, yeah, it could be viral load, but I have never seen any disease that I've dealt with or heard of where more than 50% of the people have no symptoms at all, and you have 650,000 deaths already in the United States from that disease and 4.2 million deaths worldwide. It's unheard of. You would think that a disease that can kill so many people are going to make almost everybody at least a little bit sick. But that's not the case. That's just not the case. A very unusual virus.
Well, related to that, you've seen and guided us through the HIV pandemic, through flu epidemics, and now COVID. What can we do to be more prepared for the next one?
Well, there are going to be, and are already, lessons learned, dissections, and autopsies about this, but we're already starting from a scientific standpoint. You may have heard that we put out a pandemic preparedness proposal from OSTP. Speaking of MIT, it was led by Eric Lander, who is now my colleague here in Washington, who put together a proposal that involves everything from prototype pathogen developing of vaccines to antivirals, et cetera, a massive program. That's the scientific approach. There's also a public health approach of shoring up local public health capabilities, of international security, biosecurity apparatus where you have surveillance, communication, a variety of ways that are in the public health realm. So I would hope that we don't let this terrible historic experience that we're going through, that we forget quickly what we need to do, because, I've been asked throughout my entire career, what is your worst nightmare? And I've said it, it's on the record, go back 30 years. It's a viral disease that emerges from the animal-human interface that has two characteristics. One, it's highly transmissible from person to person. And two, it has the capability of killing people at a very high rate, i.e. the 4 million people. And we are living, unfortunately, through my worst nightmare. We should not be so naive to think that we could not get something even worse than when we're going through now, where you don't have 50 to 60% of the people without symptoms, where you have most of the people, in fact, get seriously ill. That could happen.
Back to this virus, can you speak to the relative benefits and risks of choosing a specific immunogenic target, such as the spike protein?
Yeah, I mean, obviously, you want to look at that which can block infection, and the spike protein with its receptor binding domain is absolutely the critical issue in neutralizing the virus for its entry and blocking it getting into the cell by the ACE2 receptor. As with other viruses, including influenza, it isn't only the hemagglutinin that you want to block. There are also a lot of other proteins that you want to block. So there's work now going on directing against other antigens besides the receptor binding domain on the spike protein and even non-spike protein components. So even though we're focusing and have focused, I might say successfully, on the spike protein, we're not just leaving it at that. We're looking at all other options.
And do you imagine, you spoke to a variety of viral variants. Do you have any insight into whether some of these additional variants are likely to be as impactful as Delta in the future? And could we quickly modify the mRNA vaccines to deal with that?
Well, yes, there's always the threat. I mean, there's this mu variant that's hanging around that's got some worrisome mutations, but there's good news, bad news about Delta. Delta's a bad variant, but it's crowding out everything else, even those that might pathogenically be more serious. The Delta's the big bully on the block, pushing all the other variants aside. But one thing that we've noticed that's really curious, that when you boost with, for example, the third shot of the mRNA, and you increase the level of antibodies multifold, the way I showed you, you increase the protection against Delta by tenfold, even though the boost is against the original prototype virus, which is the Wuhan strain. So you can boost against one strain, and if you get a high enough antibody titer, it crosses over against all the other variants, which is really interesting. So you may not need to have a variant-specific boost, which I think would be good news, because then you'd be playing whack-a-mole with every one of the variants, which you don't want to do.
Erica has, I think, an important question. She says, I come from a historically marginalized community, and I am having trouble convincing some of my friends who have an innate distrust towards authority to get vaccinated. As an environmental scientist, I'm not sure of the best way to assuage these fears, since presentation of the data hasn't helped so far. Are there resources in place to help combat this type of reluctance? What more can I do?
Well, Erica, personally, I think you should, if you are a trusted messenger in the community that you represent, that you might want to continue, because I have seen that if you get trusted messengers in the community to not approach people who are reticent about vaccination in anything that even resembles a pejorative manner, like, why aren't you getting vaccinated? But more really reaching out and asking what the reasons are that they're not getting vaccinated, respect those concerns, and try and provide factual information that might overcome those concerns. I mean, I gave one of them in that article that I wrote for Science, where I said, one of the real pushbacks is that this vaccine was developed in less than a year, 1 year from the time the sequence was made available to the time you're having vaccines going into the arms of people. The natural conclusion is that you rushed it and you cut corners. Whereas if you explain to people that you're talking about decades of investment in research that led to that, a lot of people change their mind about that. And then also they say, well, you don't have a fully approved vaccine. Well, now we do, because we have a BLA for the Pfizer, and we're going to have a BLA for Moderna very soon. So I think it requires patience and utilizing any trusted messenger, clergy, family physicians, people in the community who are well trusted, to try and talk with people about why it's so important to get vaccinated.
Tony, I must thank you. You're an inspirational leader. Thank you for your service. We have many students here who are contemplating going into science as a career, and I'm sure you've been inspiring to them. Thanks so much for your time.
Thank you very much. It's been a privilege to be with you, and thank you for having me. Take care.